Hello, team. Thank you to the people who emailed and were asking for a little bit of extra help with multiplicity. I know that in our lessons we didn't really get a chance to talk about it in any kind of big way. And I, of course, want to be fair about assessments and stuff. And so if this was to roll around and find itself on your Chapter 1 test or somewhere else this year, then I want to make sure that it's something that we've talked about a little bit. So I'm going to try to keep this very short. And if you're watching this and listening to me right now, then that means you have found your way to the right place, which I think will end up being like my YouTube channel. You don't need to like, you don't need to subscribe. It's not that kind of YouTube channel. Just a place where I can host videos because I don't think I can do it directly on Teams. Anyways, thanks again for the people who were asking. So we're going to keep this one short, under 5 minutes. We have this idea kind of at the end of our graphing ideas. Let's scrolling up here in our notes. We talked about how do we graph with factoring. We talked about how do we graph kind of from like an equation in its general form, like this one here, where we can see y-intercepts. And then if you factor it, you can see all of the different roots and stuff. And multiplicity, the idea of multiplicity comes from that form of an equation. And so if we're going to define this word, I guess, then we're going to write it as something as like the repeatedness of a factor. And so essentially what that means is when you factor a polynomial, if you end up, for example, with 3 factors, then that's going to create 3 roots. And the multiplicity of each factor. So if we take this one, for example, let's call it x minus 1. If we have one of that factor, then there's a certain behavior that function goes through as it travels past that root. Likewise, if we have 2 of these factors, then the behavior as it travels through that root is kind of a different shape, as you're going to see. Same thing as you extend it, if there's 3 of those roots, if there's 4 of those roots, these all kind of change the shape at the root of the function. And actually, these things behave kind of in a way that you should expect. So let's take the simplest version of this. Let's, again, just kind of queue up an example here. If we have x plus 3, x minus 5, and x minus 1 as our 3 factors, and I'm, for the purposes of this video, just going to look at this factor only. It's repeated once, which means its degree up here is 1. And therefore, you should kind of expect it to behave like a degree 1 function, which is a linear function. And so that's why at this root, so this root is going to be at x equals 1. So right here, as the function travels through it, kind of if you were to like zoom in infinitely, it would be kind of in a straight line. Of course, these things are curved, and so it doesn't create an exact straight line, but that's kind of the idea, is that it's going to travel through it with that general shape. Likewise, if we change this and put a 2, I'm going to use a different color. If we go red, if we put a 2 here, then this is going to behave like a degree 2 function, which is a quadratic. And so you would then expect, if it's approaching kind of from the positive side like this, you would expect it to bounce off like the shape of a quadratic. Is it a perfect parabola? No, it's not. But that's kind of the general shape of it at the root. Again, if we could zoom in like infinitely, you would see that the shape gets closer and closer and closer to an actual quadratic. And then likewise, if we throw in a 3 here, this is going to behave like a degree 3 function at that root, which is going to be a cubic. And cubics kind of come down, turn a little bit, and then continue on. And so on and so on and so on. If you have a degree 4 function, it's going to come down and kind of like flatten out a little bit and then come back up. It's like a flattened out quadratic. Degree 5 goes through it, but it's just like a flatter kind of moment right through that root. That's going to be our degree 5. I don't know that we need to talk about any past that, but they essentially kind of like create a pattern that any odd degree function is going to travel through, and the higher the degree, like if it's 5 or 7 or 9 or 11, the flatter out it gets, right? So the next one, maybe a degree 11 would be even flatter through it. A degree 99 might look something like this, like really flat as it goes through that function, but it's still going to travel through the intercept. And then all the even functions are going to bounce off, whether from this direction or from this direction. And again, the higher the degree, the more flat this kind of gets at its, what you might call a vertex. Okay, and so if we were to graph, if we could just kind of dial this way back to our example, if we were going to graph this exact example here, we're going to have roots at -3, 5, and 1. It looks to me like the y-intercept, if I multiply 3 and -5 and -1, you're going to get 15, so it's going to be way up here somewhere. I also know that it's an odd, positive and odd degree. So I know I'm going to be ending upwards. It's going to travel through, come through, reach way up here, and it needs to end and start in different directions. So that looks wonderful. Now watch what happens when I throw some multiplicity in this last piece here. So now I know at x equals 1, this is going to bounce instead of x equals, there. It's going to bounce off of this value right here instead of go through it. And so we're going to have a bounce. Also notice that my y-intercept will have changed because it's going to be +3 times -5 times -1 times -1. So this is actually going to be -15 now as a y-intercept way down here. So it's going to bounce off that root, come all the way down, and then end and start in the same direction because it's an even degree function, and that makes sense. Let's go one step further and cue this back to like a cubic. So if you do the calculation for the y-intercept, it's 3 times -5 times -1 times, ruin this, 3 times -5 times -1 times -1 times -1 because it's cubed. So that's actually going to be +15 again. It finds itself at that same place as it did when it was just a degree 1 root. And the only difference here is that at this point, instead of traveling directly through, like in a perfectly straight line, instead of doing this, it's just going to have like a cubic bend to it. So it's going to kind of do that, if that makes sense. And that's the idea of multiplicity, that as your factors, as your roots get repeated, then the general shape of the line as it passes through the root or bounces off the root behaves kind of as you would expect with that degree function, in the same shape of that degree function. Cool. I think I went over my 5-minute time limit, but hopefully that was helpful if you found your way over here, and if not, then come and find me, I guess on Tuesday at some point, to come and ask more about it. Cool. Thanks, guys. Thanks again for asking. Bye-bye.